and the mass is attached to it, right? And then let's assume that this is frictionless, right? So this position is an equilibrium position, right? Equilibrium position when the spring is unstretched, right? So what happens when I pull the mass all the way to here, right? So I displace it by I guess this amount, right? Which I call A, and then let it go. Or it's going to do this and that, you know, about this equilibrium position, right? So we're going to have the A, and then obviously it's going to go to minus A, right? So it's going to vibrate kind of like that, right? But to describe this dynamic system, remember what I said before, how many quantity, you have to look at how many masses you have. How many masses do you have in here? One. So for each mass you have X position, right? So if I know at every given time, I know where X is, I know how the system is configured. That's why it's 1 degree of freedom. Now imagine that now instead of having one mass, I have M1, I have another spring, and I have M2, where this one is K1, this one is K2. How many degrees of freedom in here? 2, because I need the X location of this, the X location for that, in order to see how the system looks like, okay? This system is much more complicated to solve. Now, when you get to, let's say, a cantilever beam or something like this that you pull down and let go, how many degrees of freedom you think there are? An infinite number, you know, because it's a continuous system, right? So you can model this as a lot of little masses, you know, one after the other, and we're not going to get into solving those because those are continuous systems as opposed to these guys, which are called discrete systems. So we'll talk about, again, free vibration of a single degree of freedom. That means something like that has only one mass, like a mass attached to the end of a string that we pull out and let it go, you know, and then see what happens. That's the easiest way to start a vibration course. Then, and then we go harmonically excited vibration. What do you think harmonically means?
Around a natural resonance there so that it couples, right?
So a harmonic, it's like you're exciting it with a function that has an omega in it. It's like a sine function or a cosine function. That's what it means. That means you're exciting it. Some of the forces, instead of saying it's equal to 0, it's going to be equal to maybe some f cosine omega t or something like that. Then after that, what we're going to do is we say, well, how about the vibration that is under a general forcing condition, instead of being a nice looking cosine function or sine function, because it gives you kind of, even though complicated looking equations, but at least easy to understand. But what if the function is actually does not have cosines and sines? It's just a periodic function, like maybe you know, a sawtooth function like this. This is a periodic function. Is this a sine function? Is this a cosine function? But what do you know about periodic functions as they relate to sines and cosines? Do you know, remember from your math? You know, name guy called Fourier series? Does it ring a bell?
Rings a bell, but not that many.
Okay.
About it.
I just had to gauge the situation.
It's been a
So,
while.
okay. So
The bar's pretty low.
each periodic force, is periodic function, I should say, can be decomposed into a sum
That's right.
of cosines and sines, okay? That means if you know how to deal with a cosine and sine, even when you get a periodic function, that should not be a big deal. You know, you just add the solution to each one. And then, after that, we'll delve into 2 degree of freedom systems, okay? That's where it becomes very interesting because it becomes coupled equations and stuff like that. It's like when you have 2 masses bunch of springs, and then, you know, you pull them. How are they gonna vibrate? Are they gonna go towards each other? Are they gonna vibrate in phase? How is it gonna work? Well, you can't have an answer because it depends. Your answer should always be, it's what the equation, what the solution to the equations tell me is how it's going to happen. And then we'll finish, we'll obviously skip all those chapters about continuous systems, beams, and all that kind of stuff, and then go on to, and talk about some vibration measurements and application. Talk a little bit about vibrometers, and talk about accelerometers, you know, what's an accelerometer, how does it work, what information do you get from an accelerometer, and how do you deal with it, okay? And that should conclude the course. I mean, it may sound not a lot, but it's a lot, okay? In the middle of all this, obviously, we will be doing most of the equations that you will develop in this class will be second order differential equations. Most of the equations. They're not really that complex, but they are in the form of maybe let's say for free vibration it's equal to 0. Okay? M times the second derivative of x plus c times the first derivative of x plus k times x equal to 0. And your goal is, what is x? Well, it's assumed that x is a function of t, obviously. So this is your goal. How do you solve second order differential equation? And this is what we're gonna do next week, because I know some of you are kind of rusty with this stuff, right?
Yeah.
So we're gonna take a differential equation and then solve it by hand.
Sweet.
And you got all the steps written down. I mean, I spent quite a bit of time writing it down. So, but by going through it, I think hopefully it's gonna refresh everything. So we're gonna do it by hand, which involves the characteristic equation, if you guys remember, and all that kind of stuff. So I'm not gonna say anything about it right now. And then we will do it using MATLAB. And then we will use it to, we will solve it using Laplace transforms.
What?
Laplace. Well, because most of you will be taking the controls course next time, won't you?
Yeah.
So I'm giving you some tidbits, you know, to get you ready for that. So when you get there, you're not gonna say, Laplace, you know? I don't have to do it, but I think it's probably a good idea to get a little hands on it.
More information for you before next quarter.
There you go. So, let's see, this is the ABET stuff, which I always skip. This is again a tentative term schedule, which shows that the first chapter will span approximately 2 weeks. Remember, this is give or take. We'll start with fine mass vibration today. We'll continue with next week.
And so you want those problems done for next week?
No, it's not. Remember, homework is only due after the chapter is finished.
Okay.
Since we're not gonna finish it today, but I would urge you to do at least the beginning ones
Yeah,
now.
well, I already
because
have a question on the beginning.
Because there are a lot of problems, so some of them will be related to the latter part, some of them to the beginning part, and that goes on. And then obviously we'll do chapter 2, and then this, and then week number 4, remember the deal with all the classes, week number 4, exam 1.
There's exams.
So,
Of course.
are you gonna do the lecture first and then the exam?
Yes, a
You like
little
the-
bit. You always would do like 45 minutes or an hour,
Okay.
and then we do the stuff, but the week before, we go through some examples.
And I hate to ask these questions, but I'm going to, like, notes aloud or?
I think this time we're gonna allow you to have the book.
Sounds good.
Yeah, you can have the
Not
entire
necessarily.
book open.
You take home exam too?
I'm
No.
scared now, all of a sudden.
You're gonna have you're gonna have the book open, and you can have some pretty good idea what's gonna be the exam, so.
Can we still do like a little cheat sheet to kind of?
You can have cheat sheets
Okay.
too, if you want, yeah, in addition to the book.
Okay.
I didn't notice any labs listed in the.
Yes, there are
It's
labs.
down
Oh, yeah, there
below.
are.
It's
Yeah.
afterwards.
He's getting
It's
there.
coming, it's coming. It's coming.
It's not in it,
Oh, yeah,
it's just,
no labs.
we
Right,
dabble with.
tentative
some
list
things.
of
Yeah.
labs, how
Yeah.
about that, tentative
Oh,
list.
wow.
Now, they may look like big, but they are not really, you know. The first one, for example, the one that we'll be doing next week, is pretty much gonna be done in class. Right, so,
Okay.
but I want to see that you've gone through it. In fact, we will all go through it together. It's titled Solution to Differential Equations Using the Direct Method, Laplace Transforms, and MATLAB. And hopefully we'll get exactly the same answer, right? You know? Then, the following week, what we will be doing is we will do what we call a determination of frequency of vibration from static deflection of a linear spring.
Okay, so
That's
would be
another
30, right?
easy lab, okay?
And we'll do that after the lecture?
After the lecture, obviously. When we do the labs, it will be, like today, we're just gonna do lecture, right? But in days where we do labs, we'll do lecture and we do the labs also. So lab number 2, it says, if I have a spring, right? And I put a mass on it, and then it deflects, let's say, an inch or 2 inches. What we will see in the theory is that deflection just on its own, from that deflection, I can tell you how it's going to vibrate. So that's what the theory, that's what we're gonna verify. So we're going to go there and take a spring that we have no idea how it is a spring constant. You know, we put in a mass in there, and then it deflects, put in even an unknown mass. The only thing we measure is the deflection. And then we say, hey, and we would do the data reduction on the board. That way, when you go home, you don't have to go like, how am I gonna do this data, right? So we'll find a certain frequency, but then how are we gonna test if we are true or not?
Then you gotta go back into the equations.
No, I mean, you don't have to go, we'll have to test it right there. We'll pull it from there and then measure maybe 20 cycles, right? And figure out what is the frequency, and then compare that to the one that we calculate from that little equation, right? So it's gonna be a cool one. Then a third lab will involve what we call physical modeling of simple undamped harmonic vibration. This is, again, we will study just the mass attached to the end of the spring. We will vary the spring, we will vary the masses, right? And then we will figure out if the equations that we have learned about the frequency and this and that match what we are actually getting in the lab. Again, not really complex labs by any means. Then in lab number 4, we will do torsional vibration. In other words, a big, what is it called? Big disc, right, which is attached to a vertical member, very thin, and then we'll pull it from its equilibrium position, and then it's just going to rotate like this, right? Rotation. And obviously, the analogy between linear and rotation will be just like what we've learned before. What's equivalent to mass when you go from linear to rotation? What changes? Mass becomes mass moment of inertia, if you guys remember, okay? So we're gonna use that to figure out the mass moments of inertia of some different objects. Then in 5, we'll talk about MATLAB modeling of single degree of freedom natural vibration with damping. And then we'll move on again to physical modeling of single degree of freedom damped vibration. So the way we're gonna be doing damping, we're just gonna do air damping, you know, because we're gonna attach a little kind of paper plate, you know, over the mass, because as it goes up and down, at least it creates damping. And you will see in the Logger Pro, have you guys used Logger Pro before in physics, right? So we can see the trace, you know, at least on the vibration, you see how it decreases as you go from one to the other. And then we'll move back to Simulink modeling of single degree of freedom, natural vibration with damping. So this is a Simulink part of MATLAB. And then MATLAB analysis of random signal using fast Fourier transform. In other words, when you get a time signal and you want to extract the frequencies that are hidden inside, what do you do? Obviously, the idea is to do a fast Fourier transform. Most of the, if you probably have noticed that at the end of each chapter in the book, there are a lot of MATLAB codes that deal with things, okay? So for those of you who are kind of rusty in MATLAB, you can just type that thing as is, and you will see how it works. And then you can follow line by line what it's actually doing. Now homework, obviously, there is homework for each chapter. Some, I think for 1 and 2 were good. For 3, 4, 5, potentially they may change, or it may be tweaked, you know, but we are not ready yet for that. I changed, by the way, the breakdown of the thing, just to be consistent with my other classes, because this one was had 20, 35. I have no idea why I had that. So it's going to be 10, 15, 25, 25, 25.
Are
Okay?
all the exams identical in terms of not weighted, but they're all in class, all?
Well, at least 1 and 2 will be in class. You know, I still haven't decided on the final.
The final might not be,
Final might not be.
but will it be all inclusive, or will it be just the last?
It's probably going to be mostly the last part.
Yeah, okay.
Yeah.
Will MATLAB be required for the exams, like to
No,
do MATLAB?
no,
Okay.
no, no. There's not gonna be a MATLAB solution for the final, no. And as usual, you know, please, when you submit the homework, make sure you have keep a copy. And then, for the homeworks, I grade them for completion. I don't go through each detail, it's just impossible, particularly with the number of problems. So just attempt the problems as much as you can, and you get most of the points in most cases anyways, okay? And that should conclude.
Will we
this.
be allowed to use MATLAB to verify our equations
Absolutely, yeah.
on the exams?
Anytime you want to use MATLAB for something, you know, you could do that. But for exams, no. No. For exams, I think it's gonna be, just the F equals MA type of thing, free body diagram, forces, how do you get the equation, how do you solve it? And by that time, we'd have gone through how to solve it using direct, how do you solve it doing that? And in most cases, I'm not even gonna probably ask you to solve things, because the solutions are already in the book.
Okay.
So it's really just plugging in the initial conditions and all that kind of stuff. The solutions are already there, so I'm not gonna ask you to read them.
How to solve them is there, or just the answer?
They are already solved, and then they give you the final solution, but they don't give them in terms of numbers. It just gives you a second order differential equation will meet how many constants typically at the end? 2. So how many conditions do you need for second order? To involve the 2 constants, you need 2 conditions, right? And what are those conditions usually? They call them the initial conditions. In other words, what is the initial position of, and guess what? What is the initial velocity? That's all. It's always this, you know? At time t equal to 0, my mass is at x equals this. There you go, that's your x naught, right? And then at time t equal to 0, my mass had the velocity of 1 meter per second when I released it or something like that, you know? We will go through that in more detail when we get to them. So once you have those, the equations that are solved in the book, the solutions that are given in the book already have this in a more general case, right? So you should not have any issue whatsoever. Let me see how this one shows up there.
It was there.
Oh.
There it is.
Yeah.
Is it?
Now you wait to walk away.
You got it.
Coming? Okay.
You scared it.
Do you see my mouse in there?
Are you sending us the
No.
syllabus and
No.
all that?
It's on.
I put them on Canvas,
On
sorry.
Canvas.
I didn't see
Yeah.
it.
I think I put them on canvas.
Yeah.
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 We put it in the announcement.
Oh, announcements,
Yeah.
okay.
Put it in
Thank you.
All right.
Can was,
I was looking at your syllabus.
You got an email?
no, it's in the
Oh.
canvas.
Yeah, canvas, yeah.
Here, and here,
They
you
want
look
it
in the
up.
announcement.
I just haven't, I thought you
Oh,
were
okay.
an email. I guess.
All right, so let's start with the fundamentals of vibration, okay? This is chapter 1, and there are about 8 sections to this. So we'll start first with the basic concepts of vibration, and most of them are pretty straightforward. And then how do we classify vibration? And then what are the different steps that you need to take when you have a vibration problem to solve? Okay? And then we'll talk about spring elements, mass element, and damping elements. And I think before I even start, I better mention this. Any vibration system is composed of 3 components, right? First of all, you have to have a mass. You have to have a spring that has a spring constant K, and you can have what we call a damper that has a damping constant C. That's why in most of the equations in the book, you probably see M, K's, and C's, right? You probably have noticed that. M, K, and C. And you go like, what in the world, what does a mass do in a vibrating system? What does it store? What kind of energy? It's going fast.
Kinetic.
Oh,
Kinetic.
kinetic, that's right.
Okay, so the mass stores kinetic energy, right? How about the spring? What's the role of the spring?
Potential.
It stores potential energy, because remember, a spring, whether you compress it or you extend it, it has a potential energy, which, by the way, is equal to what?
KX is the force, and 1/2 KX squared is the.
1/2 of kx squared, exactly, where x is the
Distance
from equilibrium, you know, from the undeformed length or whatever, right? From equilibrium, I should say. And what does a damper do?
It resists the motion basically, and slowly brings it to.
Okay, you mean,
It's
it
constant
resists,
energy lost, right? I
it,
mean,
it absorbs some of that energy for every cycle, right? And eventually, you know, if you have any damper, eventually the vibration dies down for free vibration, okay? Now, you have a mass and you have a spring. Let's say you have a system that has a mass and a spring, but no damper, okay? So if I have a spring, a linear spring with a mass, and then I pull it down and let it go, theoretically speaking, right? Is the vibration going to be sustained? Yes or no?
Yes.
Right?
maybe not. What about gravity?
You said no damper. That would be it.
Well, gravity is already included in there,
Okay,
right? So, because what you will have, you'll have a, let's say, spring like this, right? That's nothing, right? It's undeformed length. And then what I'll do is I'll attach a mass to it. So what's going to happen?
it's gonna stretch it by.
Well, it's
more
gonna
gravity.
stretch by an amount which we call delta ST, which is the static deflection, which we call that. Now this becomes my new equilibrium position. Okay, so if I don't do anything to the mass, it's always going to stay there, right? But the moment I pull the mass a distance x to here, or a distance a, then it's going to be vibrating about that, up and down. So during the vibration, at each time, the mass is going to have a certain velocity, meaning a certain kinetic energy, and the spring is going to have a certain potential energy. But in reality, what's really going on is that the mass, as it goes through at what point does the mass have the maximum velocity, you think?
Right at the equilibrium point.
Right at the equilibrium thing, right? When it gets to here, the kinetic energy is
0.
when it gets to there, the kinetic energy is 0. What's the potential energy of the spring there?
maximum.
It's the maximum, right? And here it's going to be the maximum. So really what's happening in a vibrating system, the role of the mass of the spring, is they keep throwing the ball one to each other, right? Think of this energy, it's like, hey, I take it now, I give it back to you, you give it back to me, and so forth and so forth. Until the damper comes in and goes, okay, you guys, every time you gotta pay it something, take out some, take out some, take out some, until nothing goes on, okay? So we'll describe individually all these components. For example, after talking about the vibration procedure, we'll talk about spring elements, and then we'll define mass elements, and then damping elements. So this is kind of a good introductory chapter. And then after that, we'll talk about harmonic motion. Harmonic, anytime you hear harmonic, think of a cosine and a sine movement, okay? And then once we define the harmonic motion, then we'll talk about harmonic analysis and how we deal with it, okay? So it sounds like 8 sections is not much, but each one is huge. All right? So let's start, right? Vibration. What is the definition of vibration? Is really, just like you know it, everybody has faced vibration of one form or another. It is a motion. It is a motion that repeats itself after an interval of time, okay? Every period, you know, it repeats itself. And we call this oscillation also, okay? Examples, the swinging of a pendulum is a vibrating system, you know, it goes back, forth, back, back and forth. The plucked string of a guitar or something like that is an example of vibration. Now, the theory of vibration then deals with the study of oscillatory motions of body and the forces associated with them. Because you have to have forces, obviously, that are going to create this very special type of motion, right? And because in statics, we typically say that sum of the forces is equal to 0. And in dynamics, the general form of dynamics, F equals ma, typically yields a constant acceleration or acceleration that just changes with time. But in here, it creates accelerations that changes in sign all the time. So in one time it goes this way, then it brings it back. That's why it always points towards an equilibrium position. That's why I said this is a very special case of a vibrating system. So what are the elementary types, parts of a vibrating system? Obviously, it includes a mean to store potential energy. You need the means to store kinetic energy and a means by which energy gets lost. So you know which one is associated with which, right? So the vibrating system involves the transfer of its potential energy, that's usually in the spring, into kinetic energy, and then from kinetic to potential energy and back and forth, okay? So we can visualize this very easily. If the system is damped, some energy is dissipated in each cycle and must be replaced by an external force if a state of vibration is to be maintained. Because if it's a free vibrating system that is damped, you know what is the final solution, right? The final solution is gonna die down to nothing, right? If you want to keep the vibration going, then you have to have a forcing function that's going to keep it vibrating. Terminology-wise, remember we already mentioned something like this before. Degree of freedom. You need to know what degrees of freedom are. Is by definition the number of, I should have underlined, independent coordinates required to determine completely the positions of all parts of the system at any instant of time, and that defines the degree of freedom of the system. Now look at this one here on the left, okay? This is called a slider crank mechanism. So you got this one that cranks up and down, and you want to find out, for example, what is the position of this mass M is, right? So do you think this is a 2 degree of freedom or 1 degree of freedom?
Looks like more than one.
More than one? Why is that? How much information do you need to find where this mass is? Hmm?
I guess you're right. Only one,
Like, I could maybe use x
or theta, yeah.
or theta. But I can't say x and theta because x is clearly,
It's redundant.
it's redundant, exactly. Because if the length of this arm is L, x is equal to L times the sine of theta. So they are dependent, okay? So this is, again, a 1 degree of freedom system. That's only one piece of information that you need. This one is fairly clear, right? It's only one mass. If you tell me what x is of that mass, I can tell where the mass is, so it's 1 degree of freedom. How about this torsional system, the disk? Once it has an equilibrium position established, if you tell me how much angle it has rotated, that's enough for me to tell, to describe the system, and therefore we need 1 degree of freedom. Okay, what if it's 2 degrees of freedom? Well, this is fairly clear, you know, the one on the left in A. You have two masses. I cannot just say it's x1. If x1 is fixed, or I can figure out what x1, x2 could be anything, right? So it's not well defined. I have to also define x2. That means I need two pieces of information to describe that system, and hence we call it a 2 degree of freedom system. Likewise here you have two disks, and each one is rotating independently. So I need theta for this one and theta 2 for this one in order to figure out the exact situation. And how about this one? Why is it 2?
Two angles.
Because the mass itself, I need one information on x for the mass to figure out where the mass is. What else do I need? I need an angle theta to find how the pendulum is. Okay? Two pieces of information, and therefore 2 degrees of freedom. Now, you go to the third one. You know, you get how many masses you have? 3 masses. So to describe the system, I need to know where each one is. Meaning, I need to have 3 x's. That means 3 degrees of freedom. How about this compound pendulum here? You know, it's got 1 mass, 2 masses, 3 masses. I need information about each one. Now, which could be in the form of what? Either x1, x2, x3, or theta 1, theta 2, theta 3. Why? Because L1 and, theta 1 and x1 are linked, theta 2 and x2 are linked, etc. And lastly, the same thing, if you have 3 disks, obviously you need information about each one, and therefore 3 degrees of freedom. Hopefully by now, you get an idea at least what degrees of freedom is, particularly since we're only going to be doing 1 and 2. Okay, so, and it goes without saying that if you have a system which involves a continuous elastic member, such as a cantilever beam, as I indicated before, these have an infinite numbers of degrees of freedom, because the cantilever beam, you can think of it as made up of a lot of slices of masses attached to each other. So to find how the beam is going to deflect, it's almost like you need to know how x is for each m. Okay, that's many of them, right? So in example below, since the beam has an infinite number of mass points, we need an infinite number of mass coordinates to specify its deflected configuration, and this enters into what we call a continuous system, right? Which we're not dealing with in this class. Okay, still in section 1, all right? What is discrete versus continuous? Discrete versus continuous, just like in calculus, when we take summation here, this summation is associated with what?
Discrete.
Discrete, when all those points become nothing, becomes continuous, right? It's like a numerical analysis. You have a curve like this, that's a continuous curve. If you want to find the integral of this between these 2 points, in numerical analysis, what do? We define those into different segments, and then we say it's this area plus that area plus this area plus that area. So we turn a continuous system into discrete systems. FEA, the same thing. You're taking a continuous plate or something like that, and you're subdividing it into many elements, right? So systems with finite number of degrees of freedom are called discrete. So when somebody says it's 1 degree of freedom, 2 degree of freedom, in fact, anytime you have a physical spring with the masses attached to it, that's a discrete system, okay? Or it's also called a lumped parameter system. And those with an infinite number of degrees of freedom are called continuous, such as beams, you know. Most of the time, continuous systems are approximated as discrete systems because it's very difficult to solve the equations for continuous systems. And solutions are obtained in a simple manner, just like when we do integration, when we take a beam and maybe divide it into 3 parts or 4 parts, you know, we can get an approximate solution for that. Although treatment of a system as continuous is the ideal because it gives you the exact results, analytical methods are limited to narrow selection problems such as uniform beams, slender rod, and thin plates. In other words, the applicability of the continuous stuff is really limited to very small problems. Okay, that's section number 1, which is basic concepts of vibration. Now we move on to section 2, in which we classify the vibration. Again, most of the first chapter is really terminology. What is free vibration? Just like free convection, right? Free vibration is after an initial disturbance, because you have to have a disturbance to initiate vibration, don't you? Because if you don't do anything, if I don't do anything to this mass here, it's just gonna sit there, right? So I have to do the initial disturbance either by moving it, holding it, moving it from its initial position and then let it go, or maybe just tap it, give it a certain velocity while it was still here, or maybe pull it and give it a certain velocity before I release it. So in other words, different combinations of initial position and initial velocity. So if a system after an initial disturbance is left to vibrate, because the key thing is after the initial one, you don't touch it, you just observe it. After initial disturbance is left to vibrate on its own, the ensuing vibration is known as free vibration. No external force acts on the system, and the oscillation of a simple pendulum is an example of a free vibration, because imagine a little cord or string with a mass attached to it. At the end of it, you pull it, you let it go, you know what it's going to do. Boom, boom, boom. Forced vibration, now we can tell it's opposite the free vibration. If a system now is subject to an external force, that means the mass, if I take the mass now and I, either maybe by hand, try to force it at a certain frequency. In other words, give it an amplitude and frequency, okay? Then the big question is, how is this mass going to respond? Okay? So if a system is subjected to an external force, often a repeating type of force, the resulting vibration is called now a forced vibration. It's not going to vibrate the same way as if it was left alone. You know, it's happy when you're doing it on its own because it's right at its mood. You know, it's got its own vibration, its own things. But when you're forcing it to do something else, there are some things mathematically that happen that we're going to be talking about next week or the week after. Now, but one thing you need to know though, if the frequency of the external force, in other words, the way I'm forcing it like this, coincides with one of the natural frequency of the system, a condition known as resonance occurs and the system undergoes dangerously large oscillations. Now, why does it say here coincides with one of the natural frequencies of the system? Because is a system supposed to have just one natural frequency or more than one natural frequency? Well, we let you in on a secret. If it's 1 degree of freedom, it's going to have just one frequency. If it's 2 degrees of freedom, it's going to have 2 natural frequencies. If it's 3, it's going to have 3, and so forth, right? So keep that in mind, because we will eventually be studying the two masses attaches with spring, which is a 2-degree freedom. So as we force them, if we coincide with either the frequency of this one or this one, we are in trouble.
That's the frequency of the mass or the frequency of the spring?
It's a frequency of the mass, because it's the mass. Thank you for asking that question. The spring that we use is assumed to be a massless spring.
Okay.
And the damper that we're gonna be using is assumed to be a massless damper. The only motion, the only solution we are trying to find, this x of t that we're trying to find, to solve, is really just x associated with the mass. It's how the mass actually moves, okay? And when we are forcing the system, we're actually forcing the mass, not the spring or anything like that, okay? So again, resonance is something to be wary about. And failures of such structures as buildings, bridges, turbines, and airplane wings have been associated with the occurrence of vibration. Okay, it's a very, very, very dangerous thing. If no energy is lost or dissipated, because now we are talking about, in terms of classification, we talked about free and forced vibration. Now we're talking about what's undamped versus damped. It's pretty clear what they are. So if there is no energy lost, what does it mean? It means it's undamped, okay? And if there is energy loss through each cycle, that means you have damped vibration. So this is just terminology again. Again, under classification, sometimes we talk about linear versus nonlinear. We will not touch nonlinear, okay? It will be beyond us. But it's important when we talk about these springs in here, these springs are supposed to be linear springs. What the heck does that mean? What does a linear spring mean? It means that, yeah, you guys know Hooke's law, right? F equals kx, right? So if you plot the force versus deflection, you typically get a straight line, okay? Because after a certain deflection, sometimes you get things that go like this. We don't do that, or something that does like that, okay? We only do this, okay? So if all the basic components of a vibratory system, remember 3 components, right? Mass, spring, and damper. If all of them behave linearly, the resulting vibration is linear vibration, and that's the one that we're going to be dealing with. If, however, any of the basic components have non-linearity, the vibration is nonlinear vibration. Now, the differential equation that governs the behavior of linear and nonlinear are linear and nonlinear, obviously. And I don't know if you've attempted to do nonlinear vibration, nonlinear differential equations, but that's not fun. It's a lot of iterative techniques associated with those. If the vibration is linear, though, it's pretty good. If the vibration is linear, the principle of superposition holds. That means the solution of a bunch of things is really the sum of the solutions of the individual parts. And for nonlinear vibration, the superposition principle is not valid, and techniques of analysis are less known. So we're not gonna be dealing with them. So we talk again about linear, nonlinear. We talked about free and forced. We talked about damped and undamped. Now we're gonna talk about deterministic versus random vibration. Where does this vibration come from, right? Or how does it manifest itself, if you will? If the value of the magnitude or the magnitude of the excitation, when somebody says, by the way, excitation, it's not the response, it's how are you exciting the system? How are you trying to vibrate it, right? If the value or the magnitude of the excitation acting on the vibratory system is known, at any given time, the excitation is deterministic. In other words, if In other words, if there is a very well-defined function of time, that means it's deterministic, right? But sometimes it's random. For example, in an earthquake, how the heck do you know what that trace is? You know, it could be anything, right? So in some cases, the excitation is non-deterministic or random, and the value of the excitation at any given time cannot be predicted. An example of random excitations are wind velocity, for example. Sometimes you have gusts, you have this and that. Road roughness, how do you know? Nobody has mapped how that road roughness is going. And ground motion during earthquakes. So all those are random vibrations. In terms of traces, this is fairly clear. You know, this is a deterministic excitation. See? Nice periodic function right here as a function of time. But here, force versus time, it's all random, you know, can't make sense out of it, you know, it's anywhere. And by the way, these types of vibratory systems can be described only in terms of statistical quantities. All right, section number 3. All right, now that we know about free vibration, force vibration, damping, we know that we have 3 important components that make up a vibrating system. Now, what does a vibration analysis, entail, if you will? Okay? A vibratory system is a dynamic system. Always keep that in mind. Remember what we said when we did dynamics? When you want to describe the dynamics of something, you need to know position at any given time, velocity at any given time, and acceleration at any given time. So a vibratory thing is a moving thing. That means I will need the same thing. I need position, I need velocity, and I need acceleration. So a vibratory system is a dynamic system for which the variables such as the excitations and responses are time dependent. So the only thing is the problems that we have done before in dynamics, we say, well, you have a crate on the ground and you're pushing it and somebody is pulling it with a force of 500 newtons. You know, all that is gone. Because now these forces are periodic forces. You know, they change in magnitude, they change in sign and everything, right? It's not just a one direction force. So it's almost like you have a black box, right? Your dynamic system. You have an input here, which is the excitation, and you're trying to find the output, which is the response of the system. So this is your black box, okay? So you know what's creating the vibration, and you're trying to find out how is the system going to respond to it, okay? So how do we deal with a problem like this? So the first thing, it says most practical vibrating systems are very complex, and I totally agree. They are really complex. I mean, when we see problems that have just a mass spring attached at the end of it, you know, nobody has that, really. But I can tell you now that a cantilever beam can be modeled with something like this very easily. A bar that is just a prismatic bar that has a weight at the end of it is also a spring, you know. A simple beam with a load in the middle that you push and then you let the beam do this can be modeled like that, as we will see. So most practical problem, that means you have a physical situation and you know that your vibrating system will have what? A mass, a spring, and a damper, but sometimes the spring is not very clear, it's not very apparent. If I show you, for example, a cantilever beam with a mass attached at the end of it, and you go like, what the heck is the, what? You can tell where the mass is, but what is the spring? It's the beam that is the spring, because it deflects according to a certain way, you know? So most practical vibrating systems are very complex, and it is impossible to consider all the details in the mathematical analysis. So how do we deal with it? We start always with the simplest model possible, okay? So, and by doing so, we will only select the most important features that we need to consider in the analysis, right? Most of the behavior, of the overall behavior of the system can be determined by considering even the simple model of a complex system, and we will see an example of that very shortly. But there are 4 steps in any vibration analysis. 4 steps. The first one is called mathematical modeling. Mathematical modeling does not mean equations.
Body diagram.
Kind of free body diagram, if you will. So you're looking at a situation and you're trying to construct something that has a mass, a spring, and a damper that mimics that stuff. That's really what it is. You're looking at a physical situation and you are trying to replace it or model it using maybe a mass and a spring where there should be a spring and a damper where there is a damper. Or maybe more than one damper, maybe more than one spring. Why are we trying to do this first phase, you think? Because eventually we need to write equations. We need to do a free body diagram on the mass. You know, if I can't physically draw a spring and a damper, there's no way I can write equations, right? So the first thing is mathematical modeling. The second one is derivation of the governing equation. In other words, use F equals ma, really. When you do F equals ma, you will end up with a differential equation in most cases. So what do you need to do that? What do you need to do with the differential equation? Well, you need to solve it, because it's the solution to the differential equation that's going to tell you how that mass is going to move. And then after that, you need to interpret the results. You know, it's not like you just solve and stop, you know. Well, look at how maybe, what is the maximum amplitude? Look at the acceleration of that thing. Is it good? Is it bad? Et cetera, et cetera. So let's look at each one of these steps individually, okay? The first one is called, obviously, mathematical modeling, and its purpose, as I indicated, is to represent all the important features of the vibrating system. For the purpose, that's why I underlined that, it's really for the purpose of deriving the mathematical equations. Okay, I have to do that step in order to be able to write the equations. And sometimes, by the way, people do a very crude model and then they get an solution and then they say, let's refine it a little bit more, right? By including many different things. Example, look at this, forging hammer, right? What do you have in there? And I can't see, I didn't bring my glasses this time. So you got your frame, you got the anvil, right? You got an elastic pad in here. You got your concrete foundation or some foundation block, right? And then you got the soil underneath. So this is your physical system. And you know what's going to happen as this mass comes in and hits this anvil. What's going to happen? And then you go like, I remember from dynamics, that's impact, right? So as they do that, depending on the coefficient of restitution, the anvil is going to have a post-impact velocity, right? So that's the disturbance that you're going to create. Then what the heck is going to happen after that? Is it going to stop, or is it going to do something, or is it, you have no idea. So what do you need to do? You need to model the system. What's the simplest model possible that you can have? Well, the first one is you can maybe take the anvil here and the frame and just use it as one big block, right? So we call this the big mass M. And then it's sitting on top of what? Well, and so this is, this is the anvil and the foundation block, this entire business, right? And then because you have a soil here at the bottom, right? It makes sense that the soil would probably have a certain, like a little spring, right? and you probably will have a little damping also. Okay, so this is the crudest model of all, but do you agree that it is probably easier to write equations for this than it is to write equations for that? This is more visual, right? Because now I take, what am I solving for, by the way, in this case here? I'm solving for the, how many degrees of freedom?
Two,
Well, the first
it
one
two?
is just one.
for the, oh,
For this one here.
I can't see
I
what.
don't see what you're.
The first one is just one.
Can't
It's
see
just
it.
one.
We don't see your cursor.
Oh, you can see my pointer?
No.
Oh, darn
Second
it. You see,
one
and
is
I
two.
can't use my pointer here too. I thought my mouse was showing that.
So the top one.
It
you mean?
was.
Or the figure eight, no.
Oh, it was, but now it's
Figure
not.
eight? Yeah.
Figure B,
Maybe when I'm on top of the figure, it doesn't show. Does it show here?
No.
no.
Not even there, huh?
You probably have to take it off a slideshow.
Yeah, you're on, I think it won't slow on the
Or
slideshow,
just
you just
duplicate.
do it on,
Yeah,
Just a regular.
yeah, now,
Yes?
Yeah.
Now you can see.
yeah.
But it's,
It's smaller, so it's harder.
it's smaller, but okay.
Well,
Like
you
this,
can just
you
hit
can
the
see?
plus sign
Yeah.
on the bottom,
Yeah, you can
bottom
just
right.
Zoom in.
Zoom.
Go to
Oh,
Oh,
the
here.
Like, yeah.
100%.
Yeah, yeah.
All right.
Isn't there a way you can do it in slideshow mode where you right click on the slideshow and then you show your pointer?
Let's try that.
What's that?
If you go back and go slideshow mode and then right click, see if that works.
Slideshow.
From beginning.
I know what happened.
And
Can you
right click
right-click?
in the slideshow,
Right click here.
does a menu come up?
I
No,
can
we
see something,
cannot
but I
see
can't
because
see
Well,
it.
but
on the-
he'll
Yeah,
see
he
it
can
Yeah,
right
you
now.
should be able to see it.
Is there an option for show pointer at all?
No,
No,
not much
it's so
different
small, I
inside.
can't even see, and I didn't bring my glasses.
So
I
what
think
I-
that the side
Go-
wouldn't
Do
be-
you want-
Who's got good eyes?
Mark it
Do
up
you want
there.
better eyeballs?
The one mark.
Better eyeballs. Look. Can you see anything there?
Yeah, let's see, that is tiny.
Okay, so I've done.
How tiny do you have it in
It's
there?
120.
It's only like a 14-inch screen.
I'm assuming we're gonna pass this class.
Screen.
Maybe it's
Yeah,
one of
but
those.
most of it's in like that.
I don't know what that'll do, yeah, okay, so does that show?
Yeah, there we go.
There we
It's
go.
like a little assassin
I
dot.
sent you.
All right, there you go.
Yes,
Thank you.
little laser
All right.
dot.
Good job, Mark.
All right,
Problem solver.
That was
Very
a little
cool.
better.
Pass this
it's right there.
You're
Look at
welcome.
that. Pointer. Thank you. All right, so this is what I was talking about. How many degrees of freedom for this guy?
Yeah.
Just one.
Just one, right? Because now it's the mass, it's the displacement of the
Oh,
anvil and the
okay.
frame all at the same time, okay? And so writing an equation for this is a piece of cake,
Yeah.
right? It's no problem, and solving the equation is no problem. But that as a first model, you go like, but is it really a good model? Because there is one thing in here, which is an elastic pad. See, did I take that into account? Because really, that vibration, that velocity or that disturbance of the anvil will be first attenuated, through this guy, right? So how do I change my model? Then I come back to this. I keep the anvil on its own and then model this elastic pad by putting in another spring and another damper in there, which is attached to the foundation block. The foundation block is on its own, which in turn is attached to the ground. You see how you refine first cut model, a refined model. But how many degrees of freedom do we have here?
2.
2. So this is more complex to solve, but it is more representative of the actual one. Now, that doesn't mean that you can take it even more, right? If you want to be crazy. All right, so this hopefully, it says for the refined information, for a refined approximation, the weights of the frame and anvil and the foundation block are represented separately with a 2-degree of freedom model, right? Okay, now that we have the mathematical model done, what's the next step? Next step is to derive the equation, okay? derivation of the governing equations. What do we do with that? Well, we use the principle of dynamics, which is nothing more than sum of forces equal ma, to derive the equations. Or sometimes we can use energy methods too. You know, if there is no damping, we say the total energy is constant, and take derivatives. I'll show you all how to do all that later, and then come out with the equation. So the equations of motion can be derived conveniently by drawing a free body diagram of all masses involved. So for a vibrating system, if it's 1 degree of freedom, that implies you have one mass that you are dealing with. If it's 2, it's 2. So when you do free body diagram, you do free body diagram on the mass. Forget about the spring. The spring, you just figure out, okay, is the spring elongated? That means it's pulling on the mass this way, etc. All right, so when we do this, let's say we end up with some equations of motion, right? And it turns out that the equations of motion of our vibrating system are usually in the form of a set of ODEs, ordinary differential equations. Why are they ODEs? Because it's a function of a single variable, right? So we don't need to worry about that, as opposed to a continuous beam, which becomes a partial differential equation, okay? So in our case, we will be kind of this form, and these are ODEs. Okay, we did the mathematical model. We derived the equations by doing, hopefully correctly, the free body diagram and all that kind of good stuff. What's the next step?
Solve it.
Solve it. You don't create an equation just to look at it, you get to solve it.
How many points for just the equation?
And go like that, right? That's- Next thing is to solve. So the equations of motion should be solved to find the response of the system, because now you're nearing the end. The solution of that is going to tell you, hey, this mass is going to move according to this big, complicated looking equation as a function of time. So the equations of motion should be solved to find the response of the vibrating system. And obviously, depending on the nature of the problem, we can use one of the following techniques to find the solution. Okay? And this is kind of the topic of the first lab, if you will. You can use standard methods for solving differential equations, which I don't know how many of you remember the characteristic equation, and getting the roots, and then putting it in the general form, and then applying the initial conditions. I mean, it's kind of a boring set of steps, but anyway, it takes you to the result. Or we can do them using Laplace transform method, because Laplace transforms turn, the advantage of Laplace transform is it turns an ordinary differential equation into an algebraic equation. That's really cool. And then algebra is easy to handle than the only problem is you have to do inverse Laplace to find the time functions. But we'll deal with that later. Or you can do matrix methods, or if everything fails, numerical methods. If you've taken numerical analysis, I'm sure you've gone through how to solve differential equations, you know, Rank-Kutta techniques and all that kind of good stuff. If the equations are nonlinear, they can seldom be solved in closed form. So we're not gonna touch this at all, okay? We're only gonna deal with linear stuff. Last step, remember, 4 steps? We got now the solutions, right? So what are we gonna do with the solutions? We're gonna look at them and say, hey, let's interpret these results, okay? Because the solution will give you the displacement, velocities, and acceleration. Let me correct myself in here. When you solve this equation right there, when you solve this equation, what are you gonna get? You're gonna get x of t. That's what you're gonna get, right? Now, to get the velocity, what do? To solve for velocity?
dx.
Exactly. Once you find the x of t, then the velocity is simply dx over dt, so you're expected to know to take derivatives. And to find the acceleration, you take that, right? So in other words, if I have, by the way, if x is equal to, because these will come over and over again, okay? So if x of t is equal to a, let's say, cosine omega t plus phi, let's say. What is x dot of t equal to? Hopefully, as you go through this class, this should be quick.
Well, hopefully. Minus a sine,
Minus
a sine,
A.
omega t plus b,
sine omega t plus phi
plus some other stuff.
Plus a constant,
Plus
right?
omega,
It's a,
wait.
T, we can use the method of.
What rule should you use for
Yeah,
that?
the-
Chain
the
rule?
Chain rule.
Chain rule.
Chain rule,
Plus the derivative of the inside, right? So
Yeah.
omega.
not plus,
No,
Times.
it's
Times.
Times the derivative.
not plus, times. What is the derivative of the inside?
Omega,
It's just omega. So minus a
omega, okay.
omega.
So what was that word you used, derivative? What is that? No, I'm just kidding, sorry.
So what is x dot of t?
No, it's gonna
More
be,
fun. Minus a,
cosine.
Minus a
Oh, the.
I guess
cosine
omega t plus phi.
omega t plus phi
And now it's gonna be.
Uh,
Double omega. 2 omega.
We are
Do you-
resting. Is it
So
two
would
omega?
omega be there, and
Is it-
then,
Is
no,
it
omega
positive?
squared?
Oh, no,
Omega
that's-
squared, not
omega
omega.
squared.
because this omega was there anyways,
Yeah.
right? But then this guy has to be,
Yeah.
chain rule,
Yeah.
omega comes in, so this becomes a omega squared.
But is it still negative?
Yes.
Why is it still negative? Why is it still negative?
Derivative of sine is cosine. so
That's
the
right,
omega
because the
sine.
derivative of a sine is a cosine, whereas the derivative of a cosine is a negative sign. Alright, so if you remember this, you're gonna go a long way. Alright?
Yes.
So,
We almost failed.
What about the oddball trig versions of that, like arctangent and that kind
no,
of?
no.
Okay.
We're not gonna touch those. No,
I just want to make sure we don't need to know them, that's all.
no.
Oh, good clarification.
I just don't want to
No,
go
you're
studying
so
that
cheap.
stuff.
And other things that you may be dealing with is if you have, for example, x of t is equal to, let's say, a I j omega t. You know what j is, by the way?
Is that the unit, y
Joules?
vector, whatever?
No.
Or
No.
imaginary then, or?
That's right, complex numbers. You guys remember complex numbers?
Nope.
Minus
Yikes.
square root of minus.
Remember,
I remember in one.
z is equal to a plus jb, right? So that j squared is equal to -1. Complex number representation,
It is
remember?
complex.
This is called the real part,
Yeah, but that's
Yeah.
and this one is called the
Figment of your imagination.
imaginary part. So if you plot the complex number in this plane, this is the real axis, this is the imaginary axis. So you essentially have this, right? Where this is A and this is B, right? So I'm plotting this complex number and, okay, we'll do a little review of this. But in any case, forget about this imaginary, because we're in the math. If this is A, x of t, what should x dot of t be? A
E to the JWT.
Stay the same, and then bring T down.
So
Isn't it
JW.
log of the natural log? No. it's just-
There you go.
Yeah.
Bring all of them down, okay.
Right? Chain rule.
Yeah.
Bring the JW inside. How about the second derivative of t?
A,
It's gonna be
j
AJ squared, omega
squared.
squared.
A j squared omega squared a j omega t, and you know that omega j squared is -1, so this becomes minus a omega squared a j omega t.
Easy.
All right.
We did better on that one.
Chain rule. Chain rule is very important in dynamics, and it's going to be important here. Okay? All right, okay, we were at interpreting results. So what did we say about interpretation of results? Is the solution of the governing equations gives displacements, that's what you're solving for, but then in order to get, that's why I was doing that, by the way, because this is what you're gonna be solving for, whatever X tells you, and then but it's your job to take it one step. Take that solution, take its derivative with respect to time to find how the velocity response is, and then take an additional derivative to find what the acceleration. Why? Because as we indicated before, to define a dynamic system, you need to know information about position, velocity, and acceleration. Position on its own is meaningless. These results must be interpreted with a clear view for the purpose of the analysis and the possible design implications of the result. Maybe you don't want the mass to accelerate more than this, maybe, and then you, more than 3 Gs or 4 Gs, and then you find out that it's 5 Gs for that thing. So, problem, right? Redesign, et cetera, et cetera. Another thing about modeling, mathematical modeling of a motorcycle. This is just, again, this is the physical system, right? What do you have there? Well, you have a rider that has a certain mass. It's sitting on motorcycle. that has a certain mass.
I didn't catch that.
You got a certain mass.
Hey Google, what's your mass?
Okay. So mathematical model of a motorcycle. So the first cut model shows what? So in the first model, how many masses do you have in this system, by the way?
One.
Oh, you got
Well,
two.
in here,
Two, basically.
you have two. You have a rider and you have the motorcycle.
Oh, yeah.
So as a first model, what do you need to do? Well, you need to probably combine both of them and just say, even though really they're not gonna stay totally attached, each one would be kind of individual, but as a first model, if you wanna kinda get an idea of what's going on, you will combine here as, I can't even see what this one says. M
Mass
equivalent, maybe?
equivalent, yeah.
Okay, whatever mass equivalent is, and then some K equivalent, and then some damping because of the interaction with the ground, okay? But if you wanted to refine the model, you go like, well, this really model is not quite true because this is a one-dimensional thing. If I do this one, I'm not really capturing the angular stuff, right? Because really you have a suspension here and you have a suspension in the back. So ideally what you have is really the mass of the motorcycle, the rider, plus the mass of the motorcycle, but they are supported on two ends. So you have here, you're modeling this suspension, you know, you got the strut here, right? So you have some type of K, some type of C, some type of K, some type of C, and then maybe you will have some type of K here with the ground. And then you go like, maybe I should go even one step further with this, right? Because the problem here is that you're going from 1 degree of freedom system to how many degrees of freedom here?
Three.
Three.
Well,
See here, the rear mass, the front, you know?
Right.
So you gotta figure out how this one moves, how this one moves, and how that one moves. And that's not fun to solve this problem. But if you want it to be kind of closer to reality, then you can say, yeah, but really the rider and the motorcycle are really not moving exactly the same. You know, maybe occasionally he may bounce, right? So you need to kind of remove, look from here, what you need to remove is the mass of the rider and then put in a spring and a damper. You see how the models start from?
Kinda neat.
Why don't they show any damping between the wheels and the soil?
You could add that too.
Oh.
You want 4 to
Yeah,
be.
they just
Make it harder, come on.
they didn't wanna take it further.
I was just wondering if there's a reason why they did that.
No, there is no reason, you know, maybe it's, maybe this is just what I'm thinking, is maybe it's a paved
Solid
road or
road,
something like that, then maybe you only have, as opposed to kind of soil, you know?
Okay.
So with the spring and the damper, what represents what? Is the strut the damper and the spring is?
Well, remember, they are kind of in parallel, if you will,
Okay,
right?
so
Yeah.
it represents both?
Both, yes, yeah. Because you know, the shock and the spring, essentially. Each one does its own thing.
Probably just like
Yeah.
a visual summarization of all
Right.
springs and.
So do we have an idea now at least of what the mathematical model is? Because in most textbook problems, obviously you're given a nice mass, a little spring, and this and that. These are structured problems. In reality, as an engineer, if you're being hired to go and somebody says, oh, this darn machine is really bouncing up and down in here, in this corner, right? So you need to actually go and look at that situation and try from that physical situation, try to kind of create a model like this in order to be able to write equations and then figure out what's going on.
So is there then possibly more than one right answer? Or I mean,
Well, the
within the
more-
ballpark, I guess,
Yeah.
because depending on how you look at it or interpret, like I said,
Yeah.
if he wants to go another step
Yeah.
with the concrete and I don't, I just stop at the concrete, but I do all my equations,
Yeah.
we get two different answers. I mean, it's-
Each one will give you an answer, and obviously, the
One-
rule of thumb is the more refined,
Yeah.
the closer you're gonna get, right? But sometimes it's not worth the effort to go all that stuff in order to get something that doesn't really change much. All right, so let's talk now about the next section in which we will cover the different parts of a vibrating system, okay? So we'll start with spring elements. Okay, remember, mass, spring, and damper, okay? So each one has So let's start with the linear spring. We know about linear spring, right? A linear spring is a type of mechanical link that is generally assumed to have negligible mass. Okay? In reality, though, when people do these types of analyses and they say, well, a spring really has a mass, right? Experiments have shown that you get better accuracy if you add to the mass itself a third of the mass of the spring
In your calculations.
in your calculations, but we're not going to be doing that in this class, okay? That's just because earlier we were mentioning something about you got all these components, we are writing equations about the mass, but a damper has a darn mass too, you know, and the spring has a mass. Usually that you add to that, but the linear spring is a type which is assumed to have negligible mass and damping, so it does not have any damping at all. And the most common type of a spring that we are all familiar with is the helical spring. You know, you see it in pencils, you see it in retractable pens, staplers, etc. Several other types of spring can be identified in engineering applications, however. In fact, any elastic or deformable body member is, such as cable, bar, beam, plate, can be considered as a spring. If you remember from, I don't know, from strength of materials, right? If you have a prismatic bar, remember what prismatic bar is? Just a bar that's constant cross-section, that's subjected to a load P. I think it has a length L and a cross-sectional area A, right? So what is the stress in here? Stress is P divided by A, and then epsilon, which is the strain, is the deformation divided by the original length, right? delta L over L, where delta is, obviously after you go this is supposed to be delta, right? And if this is linear, what equation should it satisfy? Hooke's law, right? Remember in the material properties, when you plot sigma versus epsilon, if you are in the linear range before getting into plastic region, what is the equation for this? Sigma equals E times epsilon. Does that ring a bell? Where E is the Young's modulus.
Yes.
Right? So if that is the case, then if sigma is equal to E times epsilon, that means sigma, I replace it by P over A, and then I have E, and then epsilon is delta over L, right? That means that P is equal to AE, is that correct? AE over L times delta, right?
Yep.
So what is this?
Okay.
Force. This is what?
Yeah.
Displacement.
Displacement.
So this is K effective, you see?
Yeah.
So a bar that I'm just pulling in tension is like a spring. And you go like, oh, if that's a spring, what is the value of K? Well, I'll tell you what the value of K is. It's the cross-sectional area times Young's modulus divided by the length of the spring. And guess what? If you make the length longer, right? If you make the length longer, what's going to happen to K? If L goes high, K goes low, because the longer it is, the more easy it is to elongate, you know? The reason I did this is just to show you that not all springs are just regular springs. Everything could be looked at as a spring. That's why it says here, any elastic or deformable body or member such as a cable, bar, beam, shaft, I just did it for shaft here, or plate can be considered as a spring. So what else do we know about springs? Well, when a spring is stretched or compressed under a tensile or compressive force, according to Newton's third law of motion, the restoring force or reaction is minus F. Obviously, if you pull here with plus F, here, you're trying to stretch the spring with this force, and you're gonna have obviously a reaction which is minus F. But the bottom line is that this X here will be related to F by F equals KX. So if a spring is a soft spring, that means K is small, the X will tend to be large. But if a spring is very stiff, that means K is high, for an applied force, the X is going to be small. You know, so nothing out of the ordinary here. What else can we say about springs? Two key equations about springs is that F equals Kx. Remember this, right? The force is proportional to the displacement. As the spring, the more it stretches, the more the spring stretches, the more force it develops. But because we're dealing with energy also, the energy that is associated with the spring is, remember, work is equal to what?
Force times distance.
Force times distance. So if the force is Kx, so dW is the force times an elementary displacement, which is dx, right? So if you want to find the entire work, I have to do what? Integrate this between 0 and x of kx dx. If k is constant, it can come out. So it's k 0 to x of x dx. What is the integral of x dx? X squared over 2. That's why we have this as kx squared over 2. Okay? So u is equal to 1/2 of kx squared. This is called the work done in deforming a spring, which is stored as strain energy or potential energy in the spring. Now, any elastic or deformable member can be considered as a spring. In fact, if you have your book, the equivalent spring constants, if you get your book here, in the front page, right, on the inside cover of the book, right here, right, it tells you what the, let's say for example, the top one that you probably can see, it's a cantilever beam with an end load, okay? From strength of materials, we have derived this type of equation, right, when we talked about beam deflections, etc. And then it turned out that at the end, where the load is applied, you know, you have a certain deflection, right? So you take the load divided by that deflection, you should get the equivalent stiffness. In other words, the only thing you need to keep in mind is that when somebody says, what is the equivalent K, right? In order to get the equivalent K, you need to write the equation in the form of what? Load equals some whatever group times displacement, right? Whatever that group happens to be is really the K, just like I did it in here, okay? In fact, oh, they had that example here, I didn't realize this. Spring constant of a rod, right? That's almost the same thing as I did back there, maybe. It says find the equivalent spring constant of a uniform rod of length L, cross-sectional area A, and Young's modulus E, subjected to a tensile load or compressive force F, okay? So you know in this case that if you pull it, what's going to happen? You're gonna have a certain elongation, right? So, and what did we get? AE over L, just like what I have back there, okay? So this one is the same thing as this. For me, it's easier to write equations using this than it is to write equations using that, okay? So how did we get AE over L? Well, I guess it's the same arguments that I have used in my analysis, is that the elongation of the rod under axial loading can be expressed as delta, well, delta over L times L equals epsilon L, whatever. I like
No, I like whatever,
that.
Put that on the chat, whatever.
Just explain
Yours
it again,
yours is a
that's
bit more
what it is.
clear. This one.
I think mine is probably clearer.
I wrote yours down because
Yeah.
although that FLAE is from another, isn't it PLAE?
Yeah, so
Yeah.
it's-
PL over
Yes.
AE, yeah, it's, so I think just from my memory that I did this, but I think we got the same answer, so we're fine, okay? Another way of looking at this one is, again, for that thing about an end load, if you have a cantilever beam that has geometrical properties and material properties, right? Geometrical properties meaning cross-sectional area. What is I, by the way?
Is that your moment of inertia?
I think that's-
What kind of moment of inertia?
Kinetic? No.
There are two moments of inertia that I know.
It's the mass moment of inertia, isn't it?
Now, you only use the mass moment of inertia for dynamics. For beams, remember the flexure equation? I is the area moment of inertia.
Area moment,
Oh, that's
okay.
right.
Right, it's an area
That's the-
property, right? Remember BH cubed over 12, if that rings a bell? Okay, so you put an end load at the end of this cantilever beam, what's going to happen to this mass? At the end, it's going to deflect, right? So it turns out that it's going to deflect such that when if you were to write the equations, the delta is going to be equal to, LWL over something, because obviously the delta is going to be a function of W. In fact, I think the solution is here anyway, so nobody remembers these equations. So you have to look at the strength of material book. If you have a cantilever beam that has the length L, and you put the end load of it, what the cantilever beam tells you is that it's going to deflect an amount delta equals to this. kind of makes sense because the higher the load, the more deflection. The longer the length of the beam, the more the deflection, right? The lesser the area moment of inertia, not moment, the area moment of inertia, the more, etc. Now, the only thing is you rewrite this equation in the form of what? You know that K is equal to what? It's the load divided by delta, right? So you write K as W divided by delta, and here you get W from delta from here, which happens to be 3EI over L cubed. So what does this mean? This means that this physical model that you see here can be modeled as this, which is really easy, because we will be doing this a lot, and starting next week or so. How do we analyze this stuff? And we can, doesn't matter what we do with this, whether we just pull it from equilibrium and let it go, in which case it's gonna start doing this, or whether we are forcing it to vibrate, we can find solutions for those. We cannot find a solution for this directly, but for this we can. Yes?
Is this a good time to ask a question?
Sure.
So in the inside cover of the book, they have a simply supported beam with load in the middle,
Yes.
okay? They show that one,
Uh-huh.
and I was trying some of these homework problems,
Okay.
okay? And when I got to, I just wanna ask an assumption question. Now, we won't have to solve the problem right now, because
Mhm.
we haven't had it yet, but just wanna understand, for 1.56,
What's that, 1.56?
there's a system of two dampers, it's figure 1.104 and 108. The load is not in the middle, it's
1.5,
Page
1.56.
100, page 108.
page 108,
Okay,
figure 1.104.
uh-huh.
Do I assume that beam is simply supported, or is it fixed on one end as a cantilever? They don't say.
Well, it is, well, in this case, let me see what this problem is
It's
about.
considering it's just two dampers, two different constants.
Is that 158? I think.
Yeah, the rigid bar to which the two are connected remains
Yeah,
horizontal.
design shock absorber,
No, it's a 1.56.
1.56.
1.56.
Consider the system of two dampers with damping constancy arranged in this, the rigid bar is this, determine the equivalent damping. That's a total, you don't even have to use that stuff. I'm gonna show you how to do, when we get to there, where we
Where's that
combine.
into it? We're gonna combine it?
Yeah, we're gonna
Okay,
combine,
okay.
it's when we get to the part where we combine the Cs, okay?
Okay.
Because now we're only talking about one spring, okay? The big question now that we're gonna do, maybe we'll take a 5-minute break. What if you have more than one spring? What do you do? Just like in electrical
Circuit, yeah,
circuits,
yeah.
you have a bunch of resistors. So the resistors can be in two forms. They can be in series, they can be in parallel. You probably have looked at many problems in which you get a bunch, so how do you go from all that big thing into just one equivalent resistor? It's the same thing applies here for springs and for dampers. We can, like those two dampers now, can be modeled into one equivalent damper.
Okay, that would simplify it. But still, all the other problems
Mhm.
before, you had it like a cantilever beam that's fixed at one end, and you can use that equation.
Right.
This beam, I don't know how it's just floating there in space.
It's a floating in space, but it's, we'll get to that.
Okay, just checking. Never mind.
Yeah, I think it's too early to talk
Okay.
about the details of it at this
Okay.
moment.
Way to go.
Yeah, I mean, it's, we haven't even gotten to that, dampers yet, because there's one key thing about dampers to find what equivalent damping is. For a spring, the force is proportional to the displacement. For a damper, the force is proportional to the
Force.
No, to the velocity.
Ah,
That's the key. Force is, so you need to rewrite the stuff so that you get force is equal to some thing times the velocity. That big thing is going to be the equivalent C. Okay? I mean, we'll talk more about this, okay?
Okay, yeah.
It's,
okay.
all right, you guys wanna take a little breather, or do you want me to just?
Sure.
Yeah, let's take a little, not long thing.
sometimes it escapes through my mouth. One of my thoughts
I
escaped
always,
as a
I know,
mumble.
I always thinking about saying, well, that I'm talking out loud. No shit, I'm talking out loud, I'm thinking out loud, my bad. I always have to correct myself.
First 3 or 4 problems.
Yeah, I think we'll be able to do 3, 11, 22, 26. And because then we get into section 1.E.
Is that where we get into dampers and stuff?
No, it's more or less, I mean, commercial stuff. Oh, see, I'm in 1.7 right now, just doing this.
Your lecture is helping, by the way, 'cause reading this on my own, I was going, oh my god. So,
Well, it's a lot of reading to this, doing your own on this.
It's a good book.
it is a good
I
book.
like this book.
Yeah.
I like this book a lot. Last year, I tested another book, which I thought was gonna be better, but, you know, it was much thinner book.
You don't trust thinner?
Yeah. No, this guy has got more practical stuff that
Yeah.
you can see, you can visualize. you
Right.
can
No,
make
he
sense
explains it pretty
of,
well.
And that's why it's thick.
Yeah.
He explains things, he takes his time, the examples are fairly well detailed, and I like the examples that he
Yeah, that's what
puts
I'm
in.
going through right now.
So, hey, that's why I went back to it, you know?
You learned this stuff, I really don't remember. I'm just kidding.
I've completely forgotten, I've been trying to study for the FE exams.
Oh, really?
Cause I have this goal to take the FE exam before I graduate, but I have a feeling I might be taking it in August.
Cool.
Yeah, I just put my coat
Can I
back
borrow
on.
my jacket?
Yeah.
It's not very thick, but.
Yeah, so I think
Anyway.
you'll be able to do that.
Yeah, when I get to this party, I'm thinking it must be the night before I
Because
graduate.
then, it's,
And then we get into 51, which is a different section.
right.
Get drunk.
Yeah.
Yeah, we're gonna get, you're gonna celebrate getting
You'll
nuts.
be able to do 127.
I'm serious, it's a heart attack. So.
First
I'm
half.
just, of course, that
And then
means
we
we
got
have to
51,
finish the work.
56, 84, and 140.
Well, I'm not gonna be graduated by then, so I'm not
Well,
gonna
you
finish,
get
but I
to
don't
come
care.
anyway, anybody who's helping you along the way gets to come.
Yeah, might be give me an opportunity to hang out with Ken again.
Yeah.
See him online all the time, but
I actually work with Ken sometimes, which is great.
talk with him almost every day.
I can't invite Claudio because Claudio freaking moved to France.
Yeah, that's right, Claudio.
I don't know what's in the Rashi, but I'd like to find her.
Why didn't he move to Italy? I hear he's got a gravy there, they take a whole month of August off.
Yeah.
Should've just got to work for Lenient. When I was on the 87 we had all sorts of funny stories about people at Lenient. They're like totally moved to the beat of their own drum. We gotta get this done quick because August is coming up and they take that
Whole month off.
Yeah, that's cool.
Actually, all of Europe shuts down in August,
Oh, really?
except all the,
Not just, okay, so
all
maybe.
the big hotels and vacation spots, they know are doing it.
Sweet. Good.
So you don't wanna go to Europe in August because it's crowded.
No.
Are you just doing, thermal and this one and senior? Oops.
We had
Thermal
thermofluids and this. So you got control systems.
Next.
Next.
Yeah.
Yeah, after this one.
Yeah.
Alright.
And fluids too.
Yeah.
And then you're done.
What else is there? Oh, the heat transfer.
That transfer.
Oh, you gotta take
Check
these
that
out.
out. Funny.
So you're gonna be doing all the way through summer? Yeah.
The next quarter's
Strap.
so good.
Yeah, the next one. Oh, yeah.
Yes.
Yeah.
Yeah, hoping.
Seriously?
Always. That's how.
Includes to heat transfer, senior projects,
You.
and control systems.
Ain't too bad.
My son is ready to do.
You're almost done.
I'll play on that game.
The build part of it.
Film my TV.
You still gotta do the write-up.
Yeah.
Yes, but
I'm trying to get that done before.
They get
the quarter.
frustrated.
it's not gonna be one of those
You spam?
on the last day.
That's true.
Put their shit together.
Oh, they must be doing the same thing over and over and over and over.
Yeah, it was really
Yeah,
nice.
present.
This is the
It
other
was really
stuff,
nice.
like-
Me and Brittany kind of working together.
Yeah.
Off the
That's
book.
pretty awesome.
Yeah.
That, that would've killed me.
No, I'm not figuring, I figured it out.
I had one class last quarter. I didn't look at my stuff hardly at all. My mind was just focusing on thermo. Really, just one class.
SolidWorks reinstalled.
I don't know.
I gotta.
I put like
It took
at
me
least
like 4 days.
250, 200 hours into it
Salt and
on
how to get
summer.
the license.
Just got nothing else to do.
For,
So,
Katia?
No, for SolidWorks.
I don't know.
Oh. no, that was okay.
My brain's
Yeah,
not
SolidWorks.
done. It now sees the light at the end of the tunnel
I know,
next
that's-
spring for me.
It's
Or
dangerous.
next summerish, and I'm like, just focus, just do it,
Yeah.
just get it done, no
I
shit.
can't think that far ahead.
Last year this time, I was just like, am I even, I don't even wanna, can I not? This is the year now, I'm like, a year and a half, and then I'm done.
Yeah.
Then I'm done.
Dangerously close now.
Yeah, not close
I am
enough.
super focused now, and I'm like,
I'll
I'll watch the groups, I'm looking.
Yeah.
Look, we're doing this, and I'm doing this, I'm gonna stay on task.
So then the people that I forward everything I covered in the two
Well,
calls.
so here's my thought, right? If I can keep up with you, then I'm good.
Okay, got it.
Just ride her
Right,
coattails.
well, no, right now I'm actually ahead because I'm done with chapter 3 for fluids.
Yeah.
Parametric?
Barely.
Dude, that was gravy, that was
Yeah,
awesome.
he's
I
done with
love that one.
too
All
many
right, guys,
problems
let's,
today.
Hey, that's 2 more.
Cause I finally needed some.
So,
Slept the previous night.
before the break, we were just looking at the spring elements, and then we said that the simple kind of spring is just a helical spring, but a lot of other things can also be modeled as springs, such as this cantilever beam with an end load, and many other things, okay? So, but in reality though, we have situations in which springs are not, we have more than one spring in a situation. Like in this case, these two springs are obviously in parallel, right? So, and if one spring constant is K1 and the other one is spring constant is K2, what is the equivalent spring for this? It's K1 plus K2, okay? So, when two springs are in parallel, what do they share?
Displacement?
They share displacement, exactly. So if you pull, for example, with a load W, as you see here, right? If I were to do a free body diagram, what do I get? I get W that's pushing down like this, right? And then what is the force going this way?
W.
Oh.
It's K1
It's K1 times the displacement.
delta, right? Times, and this one is
K2.
K2 delta. So what can I say then? I can say that W is equal to K1 plus K2 times delta. And remember, for springs, you have to always think of Hooke's law. Force is equal to something times displacement. This is the force, this is displacement. That means that this group is the equivalent, okay? That's why we have K is equal to K1 plus K2, because if we had K3, K4, K5, etc. Okay, so when you have more than one spring in parallel, if you need to pull, if you need to generate more force, what do you need to do? You need to put more springs in parallel, because then you can hold more load, okay? So K equivalent is K1 plus K2. What if the springs are, excuse me, in series? Ah.
Series, that's what it is.
So why is this doing this thing?
Because it's
I
written.
said series.
If you say it, it'll.
Oh,
Yeah, I think
because-
it says Siri.
You can't stop it.
Series, it's always
You
series,
guys
yeah.
are gonna make everybody's.
Oh.
Can you not
phone
shut it
go
off?
Was that?
Can you not shut it off?
You can in
Ah,
the
I
settings,
can, that's right.
yeah.
Series.
Yeah. So combination
So
of
in that
springs.
word-
Spring in series. Yeah. Okay, the total, so what do they share now when they are in series? Earlier we said when they are in parallel, they share what? Displacement. When they are in series, they share, no, they share the force. Remember? If you put in the force like this, doesn't matter where you cut, it's the same force that's going through all of them, right? So because it is the same force, if you put it a load here, this force has to equal the total displacement, by the way, the total deflection will be a combination of the deflection of the first and the combination of the second. Does that make sense? So the total delta that you're gonna get is the delta associated with the first spring plus the delta associated with the second spring. So what is the delta associated with the first spring? Because we know that W is shared by all springs, that means I can say that W is equal to K1 delta 1. It's also equal to K2 delta 2, which is essentially equal to K equivalent times, which I don't know what it is, times delta static. But delta static is essentially the sum of these two, okay? Now you play around with these two equations and you will come up with 1 over K is equal to 1 over K1, 1 over K2. So this is almost like doing the opposite thing that resistors does.
Reverse of resistors.
Yeah, reverse of resistors. If you remember resistors, just think the opposite. Okay? Resistors in series, you add, no. You know, and then for the other one, it's the reciprocal, now it's the opposite, okay? So that's how you combine springs. That's enough to be said on this one. Let's just look at one quick example on this. Is, imagine here, you have a, in this figure here, you have the suspension system in a freight truck with parallel spring arrangements. How many springs do you have? 1, 2, and 3. Okay?
Oh, there's 3 on the other side too?
Yeah. But on this side, you have the suspension system of the freight truck with a parallel spring arrangement. Find the equivalent spring constant of the suspension if each of these helical springs, of course, you remember this from your machine design, sure. This is not just a regular kind of real spring. The spring stiffness for this type of stuff is a function of the diameter of each one, the number of turns, obviously, right? Modulus of rigidity, and or the shear modulus, essentially G. So you compute one for each one, right? It says, in fact, it's in the inside cover too, maybe. I don't know, that's what he said.
Helical spring under axial load.
Yeah. It's somewhere there.
Second from the bottom on the inside cover.
On the inside cover, second from the bottom. There
Yeah,
you
on the
go.
outside
Yeah,
cover, rather.
yeah. Yeah. K equivalent is GD4, 8MD cubed, okay? So since the 3 springs are identical and parallel, the equivalent springs constant of the suspension is given by 3 times this because they add up and you get 120 newtons, 120,000 newtons per meter. Okay. Now, in some applications, the restoring force or moment due to gravity is developed when a mass undergoes a displacement, okay? In some applications, a restoring force or moment due to gravity is developed when a mass undergoes a displacement, and we'll look at an example in just a second. In such cases, an equivalent spring constant can be associated with a restoring force of gravity. In other words, you don't always just have one spring in series, one in parallel, but sometimes you have to always, like, let's say, let's take a look at this example, just to kind of illustrate what they mean. Imagine you have this vertical piece in here that is pinned right at this point, right? And then you push with the force F, okay? If you push with the force F, you can probably guess what's going to happen, right? This original thing is going to rotate a certain angle, right? That means that this spring here, so you cannot say the spring is in parallel or this or that because they don't share the same force, nor do they share the same displacement. They share different displacement because there is rotation involved. But nonetheless, you can figure out what is the equivalent spring of this because it is something that I push and there is a displacement, right? So there has to be some type of equivalent spring associated with that. So what would that be? Well, if you look at this, it says a hinged bar of length L is connected by two springs of stiffnesses K1 and K2. And by the way, I urge you to kind of look at these examples, you know, as you review slowly, because it really adds to the understanding of vibration, right? Cannot do all of them, obviously. You know, in class, I had to skip some examples. But if you have time, look at the other ones, at least that we skip also. It says, and is subjected to a force F as shown, right here. Assuming that the angular displacement of the bar is really small. By the way, in vibration, and many other things, anytime you are told that you have an angle that is small, what approximation you are implied to do?
Like you multiply the angle by
The only approximation you have to remember, anytime you are told the angles are small, you're probably asked to say that sine of the angle is approximately equal to the angle. Period. And then the cosine of the angle is approximately 1. But more likely it's this. Why is it this? Is because a differential equation, if the angle is big, will involve probably a sine of that. That means that the differential equation is nonlinear, because this is not a linear equation, sine. But by making an assumption of a small amplitude of oscillation, you're allowed to do this, and then suddenly your equation becomes linear and easy to handle. Okay? So we have then this situation in which you have your bar like this, and then you have spring here, you have another spring there, and then you are applying a force F, right? And then obviously this is a length L2, L1, okay? So this is the hinge, this is L1, and this one is L2, and this is F, and obviously this is height or length L, hopefully. Yeah, that's L. Okay, when you do a free body diagram on this, as this one kind of deflects a little bit to the right, right? What kind of force do you have there? It's obviously you have F, right? But this force in here will be that and that. And if that's K2, oh, K1 and K2, okay? So what is this distance in here, you think, of deflection? I'm exaggerating this. Remember when you have something that is rotating, remember what I told you, dynamics and everywhere? Anytime you have something that is rotating about a fixed point, the distance this guy moves is equal to what? It's the length times the angle. S equals R theta. Because remember that kind of approximate, when the angle is small, obviously, right? So this angle would be L1 times theta. This one will be L2 times theta, and this distance in here will be approximately L3 times theta. Okay? So going with that thinking, this, for this to be in equilibrium after it deflects, or for any time you have equilibrium, well, when you push it this way and it is in equilibrium right here, that means that the sum of the moments is equal to 0. What is the moment created by force F? So it's FL, right? F times L is equal to
K2XL2.
is equal to K2 is equal to K1 times
L1 theta.
L1, well, with respect to this guy, right? So it's K1 L1 theta, right? Times what? K1 X1.
Times L1.
No, it's K1. Well, we call this for now X1, and this is X2, just to kind of figure it out. And this is X. K1 X1 times L1, because this is the moment arm, right? And the other one will be plus K2 X2 times L2. And then now following in here, so we don't get lost. So F, then you divide all this equation by L, right? And then you end up with F is equal to K1 times X1 L1 divided by L plus X2 L2 divided by L. So everybody is agreement with this. It's the same thing as this equation, except that we derived by L. Now, expressing F as K equivalent times X, so F is equal to K equivalent times X, because that's what we are trying to find. We are trying to find the equivalent stiffness. You always try to find the equivalent stiffness at the point where you are applying the force, okay? So K equivalent X is equal to, again, the same thing, K1 X1 L1 divided by L plus K2 X2 L2 divided by L. Now, what is X1? That's what I was telling you earlier. This X1 is nothing more than L1 times theta, right? And X2 is L2 times theta, and X3 is L times theta. Why is that? Because these angles are really small, okay? Because we're looking at just how much we are reflecting. When you replace that in here, the thetas will all cancel out, and then you will find that K equivalent is equal to this. So this is another example of how we combine springs when they are not kind of straight parallel, straight in series, but in some different arrangements, so that we can figure this out. Because this model obviously can be replaced now by just a force pushing on a spring that has that K equivalent, and whatever that solution is going to be will be the solution that you have at the top there. We're done, truly done now with springs. Right, what's the next component? It's the mass. Darn mass, okay. The mass or inertia element is assumed to be a rigid body. Okay, so mass is not something really soft or something like that, just a rigid body. It can lose or gain kinetic energy whenever the velocity changes. So it is there for storing kinetic energy, right? So the velocity is high, it has high energy, the velocity is low, low energy, and you move on. From Newton's law of motion, the product of the mass and its acceleration is equal to force. F equals ma. So that's how we relate force to mass, okay? And work is also equal to what? Force times distance, multiplied by the displacement in the direction of the force. Obviously, when the force is in the same direction as the displacement, the work is positive. When it is opposite, it is negative. And the work done on a mass is stored in the form of the mass's kinetic energy. If you have taken dynamics recently, that was in the chapter when we talked about work energy theory. Remember? W, U2 minus U1 is equal, I'm talking about T2 minus T1, right? The change in the work energy theorem, the change in kinetic energy is equal to the work done by the system. Okay, now where do we use this mass? People who do, for example, vibration of multi-story buildings during an earthquake, you got a building that looks like a very strange stuff, right? And then you go like, how is it gonna vibrate, right? Well, civil engineers look at that and say, hey, most of the masses of the buildings are where? In the floor, not in the walls, right? So what they do, if you have a multi-story building, by the way, let's say this, that, let's say I'm just taking this 1, 2, 3, 4, 5, 6, whatever. What they do is they take this one as, they take half of this wall and lump it with this up thing. And then they take half of this wall here plus half of the one at the bottom, right? And lump it into this. See what I'm saying? And then same thing in here, right? So that they can account for all the masses. And then suddenly they come from this and then they go like, well, I have a certain mass in here, I have another mass there, another mass there, another mass there, another mass there, another mass there. Obviously, if the ground shakes, what's going to happen? The building is going to shake. So how many degrees of freedom are you gonna have there? Well, you're gonna have as many degrees of freedom as you have floors, right? And then, which is a very complex thing, but this is much easier when you have this, and all of these are kind of related to some different K's in them, because you also have this vertical stuff that is going on, all the columns that you see here, it's a column. Remember what we said earlier, a column is like spring. That rod, P-A-E over L, whatever that is, that could be a spring here and a spring there. They are in parallel, which could be an equivalent spring like that in the middle. You see, you go from something really complex to something really simple, if you will, right? So this is a multi-story building subjected to an earthquake, assuming that the mass of the frame is negligible compared to the masses of the floors. The building can be modeled as a multi-degree of freedom system as shown. The masses of the various floor levels represent the mass elements, and the elasticities of the vertical members denote the spring elements. How do we combine? I mean, we talked about springs, but springs can be combined, right? And we've seen how we combine them in the form of series, parallel, and something different. Well, we cannot say we have masses in series and masses in parallel. It doesn't make sense, right? So in many practical applications, however, you may have some masses that are attached to kind of same, maybe rigid body or something like this, and you want to go like, well, why do I have many masses? I want to just have a single one. So how can I find an equivalent one? What is the criteria I have to use to find an equivalent mass when you have several masses? Well, it turns out that it's pretty darn simple, right? In many practical situations, several masses appear in combination. For a simple analysis, we can replace these masses by a single equivalent mass by equating the kinetic energy of the three mass system to that of the equivalent mass, period. So what you're gonna say is, if I have three masses, for example, the kinetic energy of this mass plus the kinetic energy of that plus the kinetic energy of this guy is equal to the kinetic energy of the equivalent mass. In other words, it's 1/2 of m equivalent times the velocity squared, okay? Example here. Imagine you have a translational mass connected by a rigid bar pivoted at one end. So this is the pivot point. Imagine you have mass M1, M2, M3 at locations A1, A2, sorry, L1, L2, and L3. One quick question for you. If you're rotating about point O, is the velocity of all these masses the same?
No,
Which one travels faster?
M1.
M1 travels faster?
M3.
Oh, sorry,
M3.
R3, right? For a given angular velocity, what is the linear velocity that corresponds to an angular velocity? Remember that famous equation? How does V relate to omega?
Is it omega squared
No, V is equal to R omega, right? Right. That's just a side equation here because, of course, here you're told that you have x dot 1, x dot 2, x dot 3. All I'm saying is that that's not involved in this problem, but if I have something that's pivoting here and it's rotating at an angular velocity omega, right?
Oh, okay, yeah.
What I'm trying to say is that if you have a mass here, M1, that is a distance L1 from here, what is V here equal to? What is V1? Well, V1 is going to be equal to R, which is L1 omega. How about if I have another mass that's in here at a distance L2? The velocity of this guy will be equal to V2 equals L2 omega. Remember, the farther you are from the center of rotation, the faster you're going, right? Now, in this case, remember what is the criteria that we have to use? The sum of the kinetic energies of all the masses, which is what? 1/2 of m1 x dot 1 squared plus 1/2 m dot 2 squared plus this is equal to the kinetic energy of the equivalent mass, which is 1/2 of m equivalent times x equivalent squared, right? So, in this case, obviously you have to choose at which point you want to combine all those masses. That's kind of the only thing. Do I want to combine all the masses to coincide with this point, with this point, with this point, or somewhere else? Okay? In this case, we're choosing that x equivalent will be, the mass equivalent will be combined so that it is just here at this point. Okay? So in this case, x equivalent squared is going to be to x1, right? So when you rewrite this equation, you find that m equivalent is equal to m1 L2 over L1 squared, this and that.
So everything, or that's all arbitrary, you just have to change how you do your moments?
Yeah.
Okay.
Yeah. So there you go. You got m equivalent, and then here, because x dot 1, x equivalent happens to be equal to x dot 1, right? But then the x dot 2 is actually linked to the x dot 1 by what I just did here. See here? This is going to be x dot 1. This is going to be x dot 2. So really, if I take x dot 2 divided by x dot 1, what do I get? The omegas cancel out, so it's going to be L2 divided by L1. So x dot 2 will be essentially L2 over L1 times x dot 1. By the same token, x dot 3 will be what? L3 divided by L1 times x dot 1. That's why you see that equation right there. See, x dot 2 is L2 over L1 x dot 1. x3 is the L3 over L1 x dot 1. Why are we doing everything in terms of x dot 1?
That's the equivalent.
Because it's equivalent for one thing, and when we write this equation here, x dot 1, x dot 2, x dot 3, everything is about x dot 1, and on the right hand one you have x dot 1, it cancels out. Then you only have the mass equivalent equal to something. Okay, so there you go. So that's how you combine masses. Remember, the only thing you need to remember is that the criteria has to be the sum of the kinetic energies of the individual masses has to equal to the kinetic energy of the combined one. Now, what if you have a different type of kinetic energy, right? For example, if you have translational and rotational masses. Remember in dynamics, we say that the kinetic energy of translation is equal to what? 1/2 of m
MV squared.
v squared. But in rotation, it is what?
I omega squared?
Exactly, 1/2 of I omega squared. Anytime you have something that is rotating, the mass becomes a mass moment of inertia, and a linear velocity becomes an angular velocity. So here, what do you have? You have the rack is traveling with what? Linear velocity, but the pinion is rotating with a rotational velocity, which is theta dot, okay? So what is my equivalent stuff? In other words, you're taking these two masses and you want to do an equivalent one. So the criteria then is that the kinetic energy here is equal to the sum of the translational plus the rotational, right? And then the equivalent kinetic energy is simply 1/2 of m times x equivalent squared. Now you equate this to that, and then you say x equivalent is the same thing as x, and then you use theta dot, which is omega, right, is equal to r x dot, it's v divided by r, and playing around, you will get that mass equivalent is simply equal to m plus jo over r squared. This is the equivalent translational mass or the equivalent rotational mass, because you can equate both of these masses to just a translational mass, or you can equate them to something that is just rotating. So each one will give you a different equivalent mass, okay? And that should do it for the masses. Now, to answer, so it's good to know how to combine masses, but we will not be doing these in most problems, like how to combine mass. You may have a homework problem on just how to do it on one, and then we call it a day. But it's important to know, after taking the vibration course, about 3 important quantities, such as springs, mass, dampers, to know how you deal with them in the event you need to get an equivalent stuff. Now we move on to our last component. The last component is a damper, which is C, right? So the mechanism by which vibration energy is gradually converted into heat or sound is known as damping. So anytime you have energy dissipation, it gets dissipated in the form, in most cases in the form of heat, but sometimes in the form of sound also. A damper is assumed to have neither mass or elasticity, because we don't want to mess things around, right? So just like spring does not have any stuff, the damper does not have any mass, and it does not have any K in it. It does not want to interfere with K, because K is doing the stiffness on its own. The damping force, and this is the key, for a spring, the force is proportional to the deflection of the spring. For a damper, the force that gets developed in the damper is proportional to
Velocity.
the velocity of the 2 ends of the damper. So if the 2 ends of the damper are moved, if there is no velocity within the damper, there's not going to be any damping, right? So a damper is assumed to have neither mass nor elasticity, and the damping force exists only if there is a relative velocity between the 2 ends of the damper. Now, what kind of dampings do we typically have? Well, it says here it is difficult to determine the causes of damping in practical system, as damping is modeled as one or more of the following types. In fact, 3 of these. The first one is really the most common one. It's viscous damping. That's the one that we like because it is proportional to the velocity. It is great. But there is also what we call Coulomb damping. Coulomb damping is, imagine you have a spring, a mass that is attached to a spring on a horizontal surface, but then the mass is actually sliding on the surface. So as it slides on the surface and there is kinetic friction, right, what do you create? create a kinetic force. So if my mass is moving to the left, my friction force is pointing to the right. As my mass tries to go to the right, my friction force changes sign and goes to the left. And in each one, there is work that is being done, which is equal to mu k times n, the normal force, times the displacement. So each time some work is being extracted from the entire energy of the system, and eventually the system is damped to nothing. And then there is also what we call material or solid hysteresis damping, okay? So I think we'll just finish this section and we'll call it a day.
Sounds like a good idea.
Sounds like a good idea?
Yeah,
All right.
I like that.
All right, so damping elements,
Are those ranked in order? In terms of
yes.
difficulty?
Commonality.
Of easiness, of
The third one is the hardest because the last one.
yeah, nobody
you know,
looks
it's
at
been
that one.
indirect.
You know, we recognize that it exists, but it's very hard to model mathematically. That's the
Okay.
problem. So they are ranked in the easiness, in the order of easiness of modeling, okay? In fact, that's what it says here, viscous damping is the most commonly used damping mechanism in vibration analysis, right? It's air dampers or fluid dampers. When mechanical systems vibrate in a fluid medium, the resistance offered by the fluid to the moving body causes energy to be dissipated. In viscous damping, the damping force is proportional to the velocity of the vibrating body, as opposed to Coulomb damping or the rest. Now, what are the typical examples of viscous damping? Well, you can probably have two surfaces where you have a film, fluid film in between. You can have fluid flow around the piston in a cylinder, or fluid flow through an orifice. That's probably the one that is typically used, you know, where you have a piston that's got a little hole in it, right? As you get a shock or something like that, you're forcing a fluid to go there. So that's why you're getting this resistance, you know? It's not going to happen immediately, right? And fluid film around a journal in a bearing. You guys are familiar with journal bearings, right? And Coulomb dry friction, as I explained earlier, is when you have just dry, you know, one surface sliding against another surface. And then there is what we call a material or hysteretic damping. Remember in material science where you have the stress versus strain curve, right? At a certain point, what happens? You reach yield point, and then this, and then obviously it does this, and you get fracture and all that kind of good stuff. But the moment you go beyond here, if you go to there, load the system to there, and then remove the load, what happens? In which trajectory should you go back? You go this way, and then you come back exactly this way, right? But if you load it such that you get a little bit of deformation, and you try to remove the load, in which direction do you unload? Remember, from strength of material, you always unload in a line that is parallel to the loading one, right? And then here you cross a point where you have what we call a residual strain, right? I know that's probably a lot.
Going back a few years.
A few years, okay. So that means because you are deforming, every time you deform, that means you are extracting energy. Let's put it this way.
So they're talking plastic deformation.
Plastic deformation, yes. You know, the moment you get into the plastic range, you are deforming, and therefore you're extracting energy. And then if you are doing that through each cycle, you're right, eventually you're gonna get nothing, right? And this is probably a good example of this for the material or solid hysteresis. This is the loading, right? And then if you get into the plastic range, obviously you're gonna deflect in that region, right? And the moment you start unloading, why are we talking about unloading? Because this is a vibrating system. Force goes and then comes back and goes, and comes back and goes and comes back. So as you unload, you're not gonna come back here. You're gonna unload this way, right? And then you have to go to the negative side because the force changes signs, right? And then you go again, deform the negative sign in here, and then unload back up, etc. So when you look at this, the energy that is inside, contained within this curve, is actually the amount of energy that you are typically losing through each cycle. Because the energy, if you recall from strength of material, is the energy expended per unit volume is simply the integral of sigma d epsilon, which represents just the an area under the curve. Let's see. How much more do we have? Should we leave this till next time, you think?
Yeah.
Have you had enough?
No.
I don't wanna overload you, that's the problem.
Too late, no, just kidding.
Well, let's stop it in here. I think it's fair for the first day. So we'll finish this chapter next week for sure, in the beginning, and then we'll do that lab, and we'll learn about how to solve differential equations by hand, how to do things by, in MATLAB, in Laplace transform, so we'll review all those, okay? So next week we'll probably be here until, yeah.
5:30.
No, not
9:50,
no.
like fluids.
Yeah, 9:30.
Yeah, that was a crazy one.
There could be some bad weather next week.
Oh, yeah.
Oh, yeah.
Well,
Class.
is that
Did you
better?
think about that Zoom or
I
whatever?
didn't think, I'm gonna look at it this weekend and see,
Yeah,
I'm
we'll
gonna go on this one, I don't know how
Seems
much,
more likely
how
next
much
week than
zooming we
this.
can do.
Do an
Yes.
independent study.
But
So Doc, in
Yeah, I'll
in
work from
that
home for work.
example you
but
gave
also-
of getting to the point of
I
class.
like the photos.
Yeah.
Does that happen in that existing?
I don't mind staying
Yeah.
on.
Wouldn't that
from
screw the
work.
whole thing up?
Yeah.
You kept going.
Yeah, I know.
Yeah,
Stick with you every
people
time?
with that